This is problem 1354. It's on page 747. A shell and tube heat exchanger with 2 shell passes and 12 tube passes is used to heat water with ethylene glycol. So the ethylene glycol is the hot fluid, the water is the cold fluid. Water enters the tubes at 22 degrees Celsius at a rate of 0.8 kilograms per second, leaves at 70 degrees Celsius. The ethylene glycol enters the shell at 110 Celsius, leaves at 60 Celsius. If the overall heat transfer coefficient based on the tube side is 280 watts per square meter per degree Celsius, determine the rate of heat transfer and the heat transfer surface area on the tube side. I need to not turn away from that problem too soon. I'll keep my thumb there. But the effectiveness number of transfer units method can be used to solve this problem just like the log mean temperature difference method. Notice we know all of the temperatures around the heat exchanger. Now, the effectiveness number of transfer units method really doesn't offer any significant benefit over the log mean temperature difference method. It's just nice to know that you can use it. I'm going to use this as a gentle introduction to effectiveness number of transfer units. So here's something you'll want to mark down. Remember I had you mark table 13.5 and table 13.4. The table's on page 729 and 732. And I told you that the table on page 732 was competition for the log mean temperature difference method. Now we're going to try and use that table to solve this problem. Okay? So turn to page 732 and look at the equations that are available. Now these equations require that we know the capacity ratio and the effectiveness. So let's just go ahead and grab those two things to start. Okay? So our goal is to find the effectiveness and the capacity ratio. All right, now, let me get some of the data written down. The heat exchanger has ethylene glycol and water flowing through it. We know it must be in a counterflow arrangement. How do we know that? Well, we know that the water goes from 22 degrees Celsius up to 70 degrees Celsius. The ethylene glycol goes from 110 to 60 degrees Celsius. So we've already solved this problem once using the LMTD method, right? How did we know that there's no way that this could be a co-current flow situation?
Because the temperature changed.
Because of the temperature change. We knew that there's no way water could reach 70 degrees if the ethylene glycol comes out at 60. If it's co-current flow, right? The hot side temperature would have to be higher than the cold side exit temperature if it was co-current. So this has to be countercurrent flow. All right. Now, if our goal is to get the capacity ratio, well, it's probably necessary, in fact, it's absolutely necessary, that we get the minimum heat capacity, or the heat, let me say this properly, we need the minimum capacity rate and we need the maximum capacity rate. So we're going to need the mass flow rate times the heat capacity on the cold side and the mass flow rate times the heat capacity on the hot side. Of course, we already solved this last example. That's the video I've lost, but I'll recreate. Okay, but let's go ahead and do this because it shouldn't be too bad. After all, on the cold side, we're told that the water flows at a rate of 0.8 kilograms per second, and the heat capacity of the water is 4.18 kilojoules per kilogram per degree Celsius. Okay, so the kilograms go away and we'll get kilowatts per degree Celsius. So we did this last time, but for the sake of this video and for the sake of your practice, why don't you grab your calculator and multiply this out again. 3.344. Thank you. And that's kilowatts per degree Celsius. Now, do you remember how we got the mass flow rate on the ethylene glycol side? Because that's not given. You remember the number probably, 1.2, right? How did we get it? Well, the key is to realize that all of the heat that flows out of the ethylene glycol goes into the water. So the heat flow rate, Q dot, from the ethylene glycol equals the heat flow rate into the water. Well, we could expand this and say that the mass flow rate of the ethylene glycol multiplied by the heat capacity of the ethylene glycol on the hot side multiplied by the temperature change of the ethylene glycol So 110 less 60 degrees Celsius equals the heat flow rate into the water. But that's just the mass flow rate of the water times the heat capacity of the water, which is the cold side, multiplied by the temperature change of the water, which is 70 less 22 degrees Celsius. So I'm sorry I'm mixing symbols and numbers, but you understand what I'm saying, right? The rate of heat flow from the ethylene glycol equals the rate of heat flow into the water. It's that simple. Now we already know this bit right here, right? We got a number for it. That's what we just calculated. That's the capacity rate on the cold side. Now notice the only unknown is the mass flow rate of the ethylene glycol, because we know the difference here. We know the heat capacity of the hot side. So we can find the mass flow rate of the ethylene glycol. It would simply be, let's see, 70 less 22 over 110 less 60, just to put the temperatures together. Okay. Multiplied by, we need a capacity rate on the cold side. And so that would be C, I don't know if it's going to be C min or C max, but let's just say capacity rate of the H2O. Now understand the CC, what I'm trying to say there is this is the heat capacity on the cold side. Let me be consistent and use C sub P on the cold side to make that clear. Do the same thing over here, C sub P on the hot side. Because there's a big difference between the capacity rate and the heat capacity. The capacity rate is the mass flow rate times the heat capacity, whereas the heat capacity is just the heat capacity. Okay, so being consistent here, this is the capacity rate of the water, so I guess what I had was okay. I need to divide by the heat capacity on the hot side. Okay, so you realize that the capacity rate on the water side is 3.344 kilowatts per degree Celsius. And then the heat capacity on the hot side, well, that was given, and that was 2.68 kilowatts, no, excuse me, kilojoules per kilogram per degree Celsius. So the degrees Celsius go away. Now, obviously, this temperature ratio is dimensionless as well, so we don't have to worry about it. A kilowatt is a kilojoule per second, so the kilojoules go away. And what units will we end up with here? Kilograms per second, right? So it's mass flow rate, just like we expect. And of course, if you plug all this in your calculator, you should find 1.2 kilograms per second, just remembering the number from last time. Okay. So now let's calculate the capacity rate on the hot side. So 1.2 kilograms per second multiplied by the heat capacity, 2.68 kilojoules per kilogram per degree Celsius. Let's see, kilograms go away again, we'll have kilowatts. What's the capacity rate? I remember it was 3 point something. Grab your calculator, please, and let's find out what the number was.
3.2.
How much?
3.216.
Thanks. 3.4. Sorry?
I had 3.204.
3.216 sounds familiar. Can I get somebody else to verify?
I got it. I changed
216, okay, all right. Kilowatts per degree Celsius. Now we can figure out the capacity ratio. In fact, I think we may have done that last time. Did we get a capacity ratio last time? I don't know if we needed it, but anyway, we can get it easily enough. So the capacity ratio is the minimum. Obviously, the minimum capacity rate is actually on the hot side, and the maximum capacity rate is on the cold side, on the water side. And it's not always that way. Seamen will not always go with the hot or the cold. It just depends on whichever one has the smaller number. So 3.216 over 3.344, we'll get a capacity rate close to 1, but plug it in your calculator, please. Let's find out what the capacity rate is.
0.96.
Okay, thanks. So 0.96. Now the other thing we need to do is get the effectiveness. Now this is sounding very familiar. We didn't go through this last time, did we? We just used the log mean temperature difference method? Okay, all right. Well, for some reason this is sounding familiar. Anyway, we should have all that we need from here, so I'm going to get rid of some of this stuff so I've got some more space. I don't want to get rid of the heat exchanger yet, so 70 degrees Celsius there. We've got the capacity rate written up here, so it should be set And you guys realize that all we've done is use an energy balance essentially to calculate the mass flow rate on the hot side. All right, so now the next thing to do is to calculate the effectiveness. Now, what is effectiveness? Well, effectiveness is the actual heat transfer rate. Guess I shouldn't have erased what I just had. We're going to use it. Oh well. Divided by the maximum heat transfer rate. Now, how do you calculate these things? Well, the maximum, let's go off here and calculate them. While we're at it, let's just get Q dot. I erased it, but anyway, we'll get it, it's easy. Should we use the hot side or cold side? It doesn't matter, right? It doesn't make any difference. Let's just use the cold side, since that's the information that was given. So we need the capacity rate on the cold side multiplied by the temperature change on the cold side, 70 less 22, okay? Now, the capacity rate on the cold side, remember the cold side had the maximum capacity rate, 3.344, and it was kilowatts per degree Celsius. 70 less 22 is what, 48? Do that right? So degrees Celsius go away. So plug 48 times 3.344 into your calculator, and let's figure out the actual heat transfer rate, Q dot.
160.5.
That sounds familiar, thank you. So 160.5 kilowatts. Now what about the maximum heat transfer rate? What is that? Well, what you do to calculate this is you use the minimum capacity ratio, or I'm getting the C's confused too, so don't feel bad if you do. You use the minimum capacity rate multiplied by the temperature difference between the highest temperature coming in and the lowest temperature. Both of the inlet temperatures are going to be the maximum difference. So we need to use Cmin multiplied by temperature of the hot stream in less temperature of the cold stream in. Now to do that, Cmin is 3.216 kilowatts per degree Celsius. The temperature of the hot stream in is 110, temperature of the cold stream in is 22, these are degrees Celsius. So now calculate the maximum heat transfer rate for me if you would please. 283? Thanks. So 283 kilowatts is the maximum heat transfer rate. So what's the effectiveness of the heat exchanger? Well, it's actually transferring 160.5 kilowatts. The maximum rate that would theoretically be possible is 283 kilowatts. So see the kilowatts go away. So take that ratio if you would, please.
Why wouldn't we use Cmax? since
Why
it
wouldn't we
gives
use
a higher
Cmax?
number?
It has to do with the fact that the capacity rate limits, it caps the maximum heat transfer rate, right?
And so we want to cap the most possible for the max?
I'm sorry?
We want to cap the most amount?
No, what we're saying is we want to find the maximum theoretical possible heat transfer rate. But it's kind of like saying, if you have a four-cylinder engine in your car, you can't go faster than a certain speed. That limits your maximum speed. Does that make sense?
Yeah.
The hill that you go down, if you go down the steepest hill possible, and yet you just have a four-cylinder engine, what's the maximum speed? That's kind of what we're saying here. That was confusing to me at
Using the
first too.
smallest C, we try to get the most, okay.
Right, because that Cmin limits, it's also kind of like the size of a container. You only have a certain size container, so you simply cannot overfill it, even if you have a fairly dense fluid. Okay, like that. Okay, so this ratio is how much again?
0.5. 0.567.
0.567. Okay, thanks. Now notice that's dimensionless as well. Okay, now let's go to page 732 and look at all these beautiful equations we have. You know why? You know, one of them is going to do us a bit of good. Remember, this is a two-shell pass heat exchanger, and remember, this is where I was telling you guys there is no equation here for a two-shell pass heat exchanger. What we will have to do is go back one page to page 730 and use the figure instead. Because for whatever reason, they don't have the equation for figure D, which is the one we would need. Okay? So figure D, if you look up an effectiveness of 0.5 or so, 0.56,
So it'd be 56.7%.
yeah, 56.7% on the y-axis, and look at a capacity ratio of 0.96. Now, the two curves we have are 0.75 and 1.0, right? And if you're watching this video, you should be looking at page 730 in your textbook, because that's where we're at. We're on figure D. All right, so on the y-axis, there's a 40% and 60%. The line in between them must be 50%. So it looks to me like we're about halfway between that unmarked line and 60. And we need to go over to a curve of 0.96. So that's pretty close to the curve that's 1, right? So my best estimate in reading this off is 1.25 or so. What do you guys think? Seem reasonable? Do you know what I'm reading off? I'm reading off the x-axis. Okay, so go to the y-axis, find 56.7%. Fairly arrogant in saying I can actually find that number, right? Going over to the curve that is 0.96, which is just a little bit to the left of the curve for 1, and then coming down to the x-axis.
We're gonna be closer to 1.5.
Well, 1.5 is right in the center between 1 and 2, right? To me, it looks like that if you read off 1.5, you'd be reading off something quite a bit higher than 0.55. To me, the 0.56 may not bring that, but you could go all the way to 1.5. I agree with you. Somewhere between 1.25 and 1.5 would be completely reasonable. Okay. So what do you guys want to use? I don't care. What
We're
sounds good to
using
you guys?
effectiveness of 56, right?
Yes.
Okay, so that's gonna be halfway between that middle mark between 40 and 60.
Yeah, a little bit above halfway between those two.
Yeah, I think it's closer to 1.5 or not be past that.
Okay, 1.5 is fine with me. The other argument I was making is 0.96 is going to be to the left of that curve a little bit, but we're splitting hairs.
Okay.
Okay, so 1.5 is fine with me. Let's just use it. Sounds reasonable. So basically, we've used these two things together on figure 1326D to find that the number of transfer units is about 1.5. Okay, that's fine. Obviously, if we had an equation, we could answer this question much more closely. I'm still looking. I haven't found one. I need to search all the textbooks I've got at home, and I haven't done that yet. So hopefully I can give you an equation to augment what's in the book, and then add one to that spreadsheet that I made. So there's our number of transfer units. Now, how does that help us? Well, going back to the problem statement, it says determine the rate of heat transfer and the heat transfer surface area. We've already got the rate of heat transfer, right? But the heat transfer surface area is something we need. Now, one last time, let's go to the equations, the ones that didn't help us, page 732, and look at the top of the table. This is where we get a whole lot of help, because the number of transfer units is actually UA over C min. Now we know the number of transfer units is 1.5. We also know C min, so we can get this UA product. Now, how did they word the problem? If the overall heat transfer coefficient based on the tube side is 280 watts per square meter per degree Celsius, so we've already got U. The question is now, what's A? How much surface area do we need in a heat exchanger? So we can calculate. All I'm going to do is rearrange this equation. I'm going to plug back in the number of transfer units to make it clear, but obviously we know the number of transfer units. So A would be equal to number of transfer units multiplied by C min divided by U. Okay? So we're almost done. That area is 1.5 multiplied by, now C min, let's see, that's 3.216 kilowatts per degree Celsius, divided by the overall heat transfer coefficient to 80, well, let me make it 0.28 kilowatts to make it easier. I'll just go ahead and convert that. Kilowatts per square meter, make sure I got that right. Yeah, per square meter per degree Celsius. So notice the kilowatts and the degrees Celsius go away. So plug this into your calculator, please. 1.5 times 3.216 over 0.28, and how much area do we get?
Where was U?
What's that?
Where was
U is the overall heat transfer coefficient that was given in the problem statement. It was 280 watts per square meter per degree Celsius.
17.2.
17.2?
Is that 0.280 or 280?
0.280.
Where was it?
17.2.
Okay, 17.2 square meters. You know what, since I have to record this video anyway, how about if we just finish off log mean temperature difference method again? It won't take us very long, and then we can compare, okay? All right, so let's do that really quick, and then we'll have it all on one video, which will be kind of nice. All right, now, we need to find out how much area we get based on the log mean temperature difference method. You guys can help me out here. Remember, what we need to do first is calculate delta T log mean, which would be the difference in temperature on one side less the difference in temperature on the other side divided by the natural logarithm of that difference in temperature ratio, right? So the difference in temperature on this side, we just take 60 less 22, and so that difference is 38. And on the other side, the difference is 40, right? So we need, we'll just take this to be side 1. So 38 less 40 divided by natural logarithm of 38 over 40. If you guys have it in your notes, please just give me that number. I think it's 39 degrees or so, wasn't it? Or just calculate it, it doesn't matter to me.
39 degrees.
39 degrees, that's what I thought. So there's the log mean temperature difference. Now, by way of review, this is probably a good thing, really. Was that the number that we actually used in the equation? Remember, this is a shell and tube heat exchanger, and so we had to find a correction factor F. How did we do that? We went to page 720, and we calculated the R and the P parameters. Remember that? Okay, so do you have in your notes what we did? Because I don't want to waste a lot of class time on this, since we've already done it once. We needed the correction factor, right? So how did we come up with the correction factor? Well, we had to calculate R and P, not R and R. So R, we had to go to page 720, look at figure 1318, and it would be B, right? Because we're talking about a 2 shell pass heat exchanger. So we had capital T1, I'll just copy this down quickly. Capital T1 less capital T2 divided by T2 less T1, where those are the lowercase. And I'll just go ahead and plug them in. Capital T1 is the shell inlet temperature, and capital T2 is the shell exit temperature. But the ethylene glycol flows on the shell side. So that'd be 110 less T2 coming out. The ethylene glycol came out at 60, divided by the temperature change on the tube side. Now the temperature on the tube side, let's see, the exiting temperature of the water was 70, the entering temperature was 22. So what did we get for R before? Do you guys recall, or do you have it?
1.0416 repeating.
1.04?
Yeah.
Okay. All right, and then P, little t2 less little t1, that's the temperature change on the cold side, over capital T1 less lowercase t1, which is the overall maximum temperature difference. So T2 less T1, this was on the water side, would be 70 less 22. And on the maximum temperature difference, those are both inlet temperatures. The ethylene glycol comes in at 110, 110, goes out at 22. So what number did we get for P again?
0.54 repeating.
0.54, thanks.
Sorry,
Okay.
545. It's 545.
545, okay. They were still splitting hairs when
Yeah.
reading off this figure, right? So then when we went to the figure, then on the x-axis we tried to find 0.55 or so, and went up to the curve for about 1, and we read off the correction factor. Now, for the sake of the video, I'll point this out quickly again. All right, so we're on this figure right here. What we're doing is reading off P equals 0.55, which is right about there. Between 0.5 and 0.6, it's about halfway between. We need to go up to the curve that's about 1 or so that we can read off the correction factor F. What correction factor F did we decide was reasonable last time? You guys have that in your notes as well? 0.94, okay, thanks. That looks reasonable. So 0.94, so all we have to do is take this 39 degrees and multiply it by 0.94. Now let's see, let me get rid of some of this and we'll be able to compare. I really wanted to compare the area we got from the effectiveness number of transfer units method to the area we got for the log mean temperature difference method. That's why I wanted to go through this again. So basically, Q dot will be equal to UA delta T log mean, but as I said, this is not quite right, because we need to put that correction factor F in there. So if we rearrange and solve for the area, well then that would be Q dot divided by U F delta T log mean. Now the heat transfer rate, would this be the maximum heat transfer rate or the actual heat transfer rate? Something good to ask. No subscript max, so it's the actual, right. So this is 160.5 kilowatts divided by U, which is 0.28 kilowatts per square meter per degree Celsius. The correction factor is 0.94, and the log mean temperature difference is 39 degrees Celsius. So the 39 degrees Celsius and the kilowatts go away, and we're left with square meters. So how many square meters of area do we need? 15.6? Now, why the heck did we get 15.6 meters here and 17, or square meters, and 17.2 square meters there? What could we do to rectify all this?
Something with the charts.
I think it has a lot to do with the charts, right? We measured, we read off 0.94 from the chart. That's not all that accurate. And we guesstimated really 1.5 number of transfer units. Both of these were pretty bad. So it's not a surprise. I'm glad they're on the same order of magnitude, okay? They're both about 15 or 20. That's pretty darn good. I think we did a good job solving this. Now what would really help us is if we had an equation for the number of transfer units from the effectiveness number of transfer units method, then we'd be a lot closer, and that's why I want to find one of those. Now, here's my point in all of this. My opinion is that the effectiveness number of transfer units method is better than the log mean temperature difference method because we have equations to relate the effectiveness, capacity ratio, and number of transfer units. We don't have to guess most of the time, right? We don't have to read off of a chart. If you want to use the log mean temperature difference method, you will always have to read F off of a chart. We don't have an equation for those. Okay? So my preference, if you have a choice, is to always use effectiveness number of transfer units. So the last time I'll remind you, please write at the top of page 732, table 13.5, that you would use that instead of the log mean temperature difference method. Okay? And this is for designing a heat exchanger or selecting a heat exchanger. The other note I want you to write is on page 729. It's for selecting a heat exchanger, if you're asking on 732. 729, that table is for predicting the exit temperatures of a heat exchanger. These two tables use the same method, but they're inverses of one another. Okay? Any questions?